Hello. Today I'm going to talk about the unmanned aerial system preliminary design. So as we discussed earlier, any type of aerial system, specifically the fixed wing concepts, are made of different components, including the wing, fuselage, tails, and the landing gears or other extra components that those aerial systems they may have. So we also discussed that there are 4 different phases in the design and manufacturing of unmanned aerial systems. The first one was the conceptualized design, that we actually determine the configuration of our aerial system. The second phase is a preliminary design, which is the focus of this lecture. The third phase is exact design, and the last phase was manufacturing and the flight testing. So regarding the preliminary design, here we have made this table. We have this table here, which talk about the design objective and example of the priorities for various aircraft designers. So for example, these are the components that we need to consider them once you want to design different types of aerial systems. So for example, cost, performance, flying qualities, period of design, beauty, maintainability, productability, aircraft weight, disposability, and steel properties. So these are the different components that we need to consider once you are designing different types of unmanned or manned aerial systems. So for example, for military designer, these figure of merits are different with the large civil transport designers or a small actually glider designers or home built designers. So these are, we can be a designer of different types of aerial system, from military to home built airplanes that can be drones. So each one of these factors that you will see here, it has a rate once you are considering this type of aerial system. So for example, for military aircraft, the cost actually has a rank of 4. Or for example, for a home built designer, the cost is going to be lower, so is equal to 1. So between these 4 types of airplanes, usually military designer has higher cost than the larger civil transport designer, and then followed by glider or home-built airplane. So from the performance point of view, we know that the civil transport aircraft that should have the higher performance, followed by home-built designer, and by the glider, small glider designers, and by military. Flying quality is another concept, as another factors that we are considering. So home-built designer, usually they have the higher qualities. Period of designer, here we also have 5 for military, 9 for large civil transport designer. We have 8 for small GA designer, and we have 6 for home-built designer. So for a beauty, for military design is 10, for larger civil is 7, for a small GA designer is 4, and for home built designer is equal to 5. And the same for the rest. If you talk about stealth property, we usually have the stealth property for military aircraft, that we want to avoid them to caught by different types of the radars. So this is the reason that here for military designer, we'll consider this, and this is equal to 3, and for the other airplanes is equal to 0, because we don't think about making them to have stealth properties. So here the first thing which we are going to talk about that is the wing geometry of any type of aerial system. So we have different types of airplanes that we discussed about them, including the fixed wing, flapping wing, multi-rotors, and other types of drones or aircraft systems. So what we discussed earlier, in the flapping wing drones, which they are inspired by birds, or in the fixed wing drones, so we have the wing. which the wing is responsible to generate the aerodynamic forces. So now if we compare the wing of the airplane with the helicopters or multi-rotors, so in those type of drones or unmanned or manned systems, we no longer have the wings. For example, in helicopters, we don't have wings. So the rotor or the blades of the helicopters or the rotors or propellers of multi-rotors like quadcopters or hexacopters, they are responsible to generate the lift and the thrust in the same time. But in the fixed wing and the flapping wing airplanes or drones, the wing is responsible to generate the aerodynamic forces. So here we need to know what is the wing. So here I'm going to show you an example of the airplanes that we had here. So if you look at this airplane consists of the wing, fuselage, and other types of other components. So here, this is a wing, which the wing is responsible to generate the lift force for us. So there are, before going back to the presentation, I want to show you the different geometry of the wing. So this is the top view of the wing. We also have the side view, and we have the front view of the wing. So these are the different components of the wing and different aspects of the geometry of the wing, which I'm going to talk about that. So let's go back to the presentation and talk about the wing geometry. So for the top view of the wing, we have different parts and different components, which we are going to discuss that. So the first one is a wing shape, or called planform. So for example, this is a rectangular wing shape for airplane, or if you remember, I showed you another airplane which has a delta shape. So we can have a varieties of the wing shape for our airplane, as we see here. So for example, this is a simple rectangular wing shape with actually some rounded part in the wing tips. So here, the wing shape or planform, this is the main thing which is important. The second component at the top view of the wing is called aspect ratio. So I'll talk first about all of this, and I will go one by one of these parameters and discuss more deeply about them. So then we have the taper ratio, we show with the lambda. We have the wingspan B, we have the chord lengths, we have the root chord, we have the tip chord, we have the wing area or wing surface, we have the sweep angle, and we have the mean aerodynamic chord, which we show with the MAC. So now if we consider that this is the wing of an airplane, so from this tip, from both sides at the left or right side of the wing, so the distance between these two tips is called wingspan, is the largest distances between the chord at the tip of our wing. So for example, the wingspan of this airplane that we have here, it is from this point, from this point to the end of the other point. So the largest horizontal measurement that we can have for our wing. So this is called wingspan. So going back to the presentation, we also have the chord lengths. So these are all chord lengths of the wing. These are all chord lengths, as we can see here. So the chord lengths at the middle of the wing is called root chord. This is the root chord we show with the CR. And the chord lengths at the end, we will call them tip chord, which we see here, we will show with CT. So now if I want to show you here, this at the middle part of the wing, this part, if I separate the wing, actually the wing is attached to the body. And for this case, so this is going to be a tip chord. It is going to be a root chord. And this part is tip chord. So this part is tip chord. So I want to also show you the other airplanes that we have here for the root chord and the tip chord. So if you will see here, this is going to be the root chord of the wing. Since this is actually integrated to the body, we can also consider the from here to here as our root chord, and this part is called tip chord. As you can see, this is a actually tapered wing shape, or wing shape with a sweep angle. So here, this is a shape totally different. So from here, this tip to this tip, the horizontal distance is called wingspan. This length is called wingtip, this length, and this length we are calling root chord and tip chord, right? So going back to the slide, we have also other parameters, which is called aspect ratio and the surface and the taper ratio. So the aspect ratio is one of the important geometry which affect in the aerodynamic efficiency of our system. So the definition of the aspect ratio, before talking about that, we talked about the wingspan. So the wingspan was the distance from the tip course from left to right. This was the wingspan. So the wing has also wing surface or wing area. So the surface of this rectangle is, for example, the wing area of this rectangular wing shape. So the aspect ratio is defined as, so if you want to define the aspect ratio, is defined as, so our wingspan is B, is our wingspan square divided by our surface area, which is equal to S. So this is one of the important parameters that we usually consider that once we wanted to design any type of aerial system. So today we just talk about design of the wing, which is the main part of our design process. So the other parameter, so in case that if I have a rectangular wing shape, so my root chord is going to be equal to tip chord or equal to the chord, right? Because it's rectangular. So any cross section here, it has the same length. So this is equal to this is equal to this, because it has a rectangular wing shape. So for rectangular wing shape, the aspect ratio is equal to B squared over S. But we know that here the surface area of our wing, S, is equal to B times C, right? This is a B, the length, this length times this width. It gives us the surface area of the wing. So B times C. So now this square cancels B. So this is going to be B over C. So here we can say that for rectangular wing shape, the aspect ratio is going to be wingspan divided by chord length. So this is something with a different notation that we can see here. This has been considered as a wingspan is equal to S and surface area as A. So it's exactly like this equation, but with different notation. So we also, the other parameter which is important is called taper ratio. So now what is the taper ratio? So the taper ratio is the ratio of the wing tip or tip chord to the root chord. So for example, if we define as TR, so I can say the TR, which is the taper ratio, is equal to tip chord, which is this chord we show with the CT, divided by root chord, which is equal to CR. We show with the TR or sometimes with lambda. So this is another geometry. So for example, for this tapered wing shape or with a sweep angle. If I divide this, which is my CT or tip core, if I divide it by this part, which is my CR or root core, so CT divided by CR, I'll get the lambda or taper ratio. So these are other parameters that I'm going to discuss them a bit more, deeply in the next slide. So, but to just show you the geometry of the top view of the wing. So now if we look at the front view of the wing, see what we will see. We have the dihedral angle and we have the unhedral angle. So imagine that this is your airplane, this is a fuselage, and you are looking at your airplane from the front view. So for example, this is my airplane and this is the front view that I am looking at the wing. So what we can see from here, there are two angles from the front view, that if this angle is upward, this angle is called dihedral angle, and if this is a downward, so for example, if this is my horizontal line, this angle, which is equal to this is called unhedral angle. So what is the rule of this? Why we are adding this angle to our wing from the front view? This is something that we will talk soon. So the other view is a side view, which is one of the most important part of our of the geometry of our wing, which is airfoil. So airfoil is the cross section of the wing. So for example, if we look at this airplane from the side view from here, we will see some structure like this, which this is called airfoil. So in one lecture, I'm going to discuss more details about the airfoils and about airfoil design as well. So in order to have a better view of airfoil, I'm going to show you another airplane which has a better view. So if you look at this airplane, so this is an airplane. So this is the top view. This has a delta shape. So this is going to be tip core, root core, this part, the middle. This part is going to be tip core. This divided by this, it gives me the taper ratio. So now if I look at from the side view, we don't see any angle for our wing to become actually tilted upward to have a dihedral or unhedral angle. But the good thing here is I can show you here this shape of airfoil. So this shape is the airfoil, which is responsible to generate the aerodynamic forces. So if you want to see it more clearly, so this is the shape that we will see here. So this is a cross section of the wing. For each part, I have this shape, which is my airfoil. So now let's go back to the slides. And this is the shape of the airfoil. The airfoil has a camber, has a thickness, and has a twist angle. So this is something that we usually see in the side view of the wing. So I am going to discuss about all of this in future with more details, specifically once we get to the simulation software. So here, this was the wing, right? So as we said, the aspect ratio, this is the wingspan of the wing. I just connected the two tip cords together, this horizontal line, it gives me the wingspan. So this wingspan divided by surface area, it gives us the aspect ratio, as we can see here for this actually wing shape, which is a tapered wing shape, and this is a simple rectangular wing shape. So now in these slides, I'm going to talk with more details about the wing shapes and each one of these wing geometries. So first, factors that we have from the top view of the wing was the wing shape or planform. We call planform specifically for micro drones or micro aerial vehicle which they are fixing. So for example, this wing shape that you can see here, it is going to be a delta wing shape. The shape of the wing is delta. For the other airplane that we talked about that, for this airplane is a simple rectangular wing shape. So this has a rectangular wing shape. And for this one, it has a swept back wing shape. So why airplanes they have wing shape, why wing shape is changing? There are different aerodynamic reasons that we'll talk with more details about them, in future. So going back to the slide again, these are the wing shapes. There are, you will see a different wing shapes for fixed wing micro aerial vehicle drones. So you see that this is called Zimmerman, or you can have an inverse Zimmerman. So actually in this geometry, we have half of the ellipse. So one ellipse is here, the another ellipse is here. So these are two half ellipses. They are actually making the Zimmerman or inverse Zimmerman planforms. So then this ratio of these parts of their core lengths or the radius are different. So they are not the same. So otherwise you'll have the elliptical wing shape since we have two half ellipses with different radius. So here we have Zimmerman or inverse Zimmerman wing shape. So there are varieties of the wing shape that have been inspired by birds or by combination of different geometries, and we can have a varieties of wing shapes or planforms. So actually birds sometimes give us a good view to design new wing shapes. So for example, I have these two wings. One of them is a black wing, the another one is the white wing here that we discussed earlier. So we can get inspiration from this shape of the wing, and we can actually make a new shape for the wing of our drone. So here, these are the different wing shapes for the airplanes. So that this is a taper leading edge, straight trailing edge. So this is the leading edge, and this part is trailing edge. So this is a taper at the leading edge, but this is a straight at the trailing edge. This is a taper in the leading and in the trailing edge. So the front part of the airplane, if I want to show you here, this front part, this is called leading edge, and this part at the end, this is called trailing edge of our wing. So here, going back to the slide again, this is a tapered in the leading. You see that this has an angle, it's not straightforward. So this is a taper in the leading edge and trailing edge. This is a delta wing. This is exactly like a delta. This is a sweep back wing. So this is a back which has been moved to back. So this is called sweep back. I'll talk with more detail about that today. So this is an example of the sweep back wing shape that you will see here. So this is a straightforward leading edge and trailing edge, or a straight rectangular wing shape. And this is a straight leading edge and tapered trailing edge. So this is a tapered trailing edge, and this is a straight leading edge. So these are the different wing shapes that we can have. These are some unconventional wing shapes that have been inspired by birds. And we can see that how we can make new wing shape based on the characteristics that we want or the efficiency that we need to our drones to have. So this was a wing shape. Now the second parameters that we talked was aspect ratio. We define aspect ratio as our wingspan of the wing square divided by wing area, or B square divided by S. So for example, if you compare different aspect ratio, this is an airplane with a wing with a low aspect ratio. See that the shape of the wing is fat. This is a moderate aspect ratio, and this is a high aspect ratio, which we have a narrow wing shape. We have a long wingspan. So to just show you, I have these three examples here. This is a wing shape with the high value of the aspect ratio. This is a wing shape with the moderate aspect ratio. And this example was a low aspect ratio fixed wing drone. So these are the three different aspect ratio that we have for our groups. So the main reason that aspect ratio is changing, there are different reasons. So any type of the airplane or aerial system, they have different range of the aspect ratio. So for example, we increasing the aspect ratio usually increase or the lift coefficient. The lift coefficient is coefficient that is actually characteristics of our wing to generate the lift force. This we will discuss more detail about this parameter, which is the lift coefficient, and the angle of attack, which is the angle of our wing. So here the high aspect ratio usually used in a glider, because gliders, they requires to have the high lift to drag ratio. Aircrafts that they want to fly longer range or with the high endurance, they usually also have the higher aspect ratio. So now, if you want to discuss this in more detail, I showed you these three different airplanes here. This is the first one, this is the second one, and we also had the third one. So between this wing, since it has a higher aspect ratio, it can fly further. It means that it has higher range of the flight. Also, it can fly in a longer time with the higher endurance, again because of the higher value of aspect ratio. And also it can glide, right? So it's like a glider that they have the higher values of the wing shape, so they can actually do the gliding. So this is a comparison between this wing shape. So this airplane or this drone has the lowest aspect ratio. So here it means that it would fly in a lower range compared to this larger size wingspan, or this drone with a higher aspect ratio, and this would fly also with the lower endurance because it has lower aspect ratio. So going back to this, so this was the main reason that why are some airplanes that have this higher value of aspect ratio, because the main reason to have this high lift to drag ratio or having a long range or higher endurance is because the lift coefficient is increasing and our airplane can carry more weight and it can go actually easier than the wings with the lower aspect ratio. So these are the range of the aspect ratio that I'm going to show it to you. So for a hang glider is equal to 4 to 8 as the range of the aspect ratio. For the glider, we have the maximum aspect ratio is changing from 20 to 40. It means that the wingspan square divided by the surface area is between 20 to 40. For home-built airplanes, is between 4 to 7. For general aviation, is between 5 to 9. For jet trainer, 4 to 8. For low subsonic transport airplanes, is between 6 to 9. For high subsonic transport, is changing from 8 to 12. For supersonic fighters, 2 to 4. For tactical missile, is 0.3 to 1. And for hypersonic aircraft, is 1 to 3. So now if you compare the airplanes, some of them, they have the higher value of the aspect ratio. Some of them, they have the lower value of the aspect ratio. There is a relation between the speed of our aerial object and its aspect ratio as well. So for example, if we consider an airplane which is flying like a glider, so we need to have a less drag since we don't have propulsion system and they are just reliable on the gravity acceleration. So our system should have the higher value of the aspect ratio to reduce the drag force and increase the lift. But once we want to go faster and have a more maneuverable airplane or aerial vehicle, we need to have a lower aspect ratio. So once we increase the speed, so the aspect ratio is also reducing. So for example, this is the main reason that for supersonic or hypersonic aircraft, the aspect ratio is less than subsonic airplanes, which they are flying in a lower speed, or compared to general aviation, or for example, compared to glider or hang glider. So this is the difference between different types of the airplane, that they are supposed to do different types of the mission, and this value or this parameters of the geometry of the wing is changing. So from the top view, we said also we have the taper ratio, which is the taper ratio is defined as tip chord divided by root chord. We said that we are showing the TR, or also with the lambda, which is the tip chord divided by the root chord. So this is one of the rectangular wing shape that if you see from here, the tip chord is equal to root chord. For example, this is my root chord, and here the taper ratio is equal to 1 for this case. This shows a space shuttle compound. So we'll see that the taper ratio is going to be this length divided by this length, is a component of two parts actually. So we have a lambda 1 for this part divided by this, and we have lambda 2 for this part divided by 2. So this is the F18 blue angles. So here we'll see that this divided by this, it gives us a taper ratio. This is a delta, part of the delta wing shape. These are the half of the wing shape actually. It's going to be almost 0 divided by this, or taper ratio so has a small value. And for this Boeing 747, the taper ratio is going to be the CT divided by CR. So the lambda, or the taper ratio, is changing from 0 to 1. So here we'll see that for this rectangular wing shape, this length or tip chord is equal to root chord equal to tip chord. So the lambda is equal to 1 here for this case. For this case is a number between 0 to 1 for this tapered wing. These are called tapered wing shape, as you have here. It's called tapered wing shape. And for this triangle wing shape, or delta wing shape, or lambda is equal to 0. So now I just want to ask you this question. Do you know any system in the nature which the taper ratio is more than 1? So for these cases that we saw here, the taper ratio was changing from 0 to 1, but in the nature we have some concepts that their taper ratio is more than 1. So these are the butterflies. So if you look at the butterflies wing shape, which I want to show you now in the Google, these are the butterfly wing shape that we'll see that the length of their wingtip of tip chord is more than root chord. So in this case, the lambda is more than 1. So these are some type of natural organisms or species that they have a higher value of the taper ratio, more than 1. So the taper ratio is changing from 0.1 to 1 for usually the airplanes, but for flapping wing drones, specifically the flapping wings, that their wingspan is inspired by butterflies, so their taper ratio is more than 1. But for the drones that we are designing specifically for fixed wing drone, this ratio is going to be less than 1. So now going back to going to next slide. We have also the sweep angle, which is the angle that our wing has from the top view. So what is this angle and how this change? I'm going to talk about this. So this is a tapered wing shape. As we can see here, our tip chord is not equal to our root chord, so they are different. And here, if we connect the 25% of our tip chord, so let's say that this length is our root chord, and this length is this part, or this point is at the 25% of this root chord from the leading edge, and this part is 25% from the tip chord from the leading edge. So now if I connect this line, to this one, as this dashed line that you can see, the angle that this dashed line has with this horizontal line is called sweep angle. So this is a sweep angle. So if you look at the military aircraft, they usually have angles which is swept back. So we talked about different types of the windshield earlier, that some of the airplane, they have the sweep back, some of them they are sweep forward. So we'll show them here actually in this lecture as well. So we'll see that how for sweeping airplanes or for a straightforward wing shape without sweep angle, which you show with the phi, how the lift coefficient is changing. So this shows an airplane which is sweep angle is changing. So for this case, the wing, it doesn't have any sweep angle, because if I connect this part to this part here in this case, the sweep angle is equal to 0, but once the wing is swept to the back, so a quarter of this, if we connect to quarter of this, so this would have this angle which has a sweep back angle or a sweep angle. So what is the main characteristics of, or main factor, the main reason have adding this angle to our airplanes is that, so for the airplanes that they have no sweep angle, or they have the straight wing, like the simple rectangular wing shape, so in this case we have the higher value of the lift, but we have the less speed. So you see that the lift coefficient here is higher than in this aircraft which has a sweep angle or sweep back wing. So the CL max, which is the maximum lift coefficient in the straight wing, which we need the high lift and the lower speed, is higher than the swept wing airplanes, which they need to fly with a higher speed, and they have this angle. So this is just, I want to show you the main difference between the wing with the sweep angle or without sweep angle. So going back to this two samples that we have here, this airplane, it doesn't have any sweep angle, so it would flow, it has a higher lift coefficient and flow slower than this airplane, which, as we can see here, is sweep back. So there is an angle here. So if I connect a quarter here of the wing to the quarter of here, so this would create an angle with the horizontal reference that I have. So in this case, so my drone has higher value of the sweep angle. It has a sweep angle. So in this case, it has the less value of the lift coefficient, and it should fly faster to get enough lift. So the next parameter that we want to discuss is the standard mean chord, is the average actually chord length. So if we said that this is a root chord and this was a tip chord, and we will see that the tip chord, the chord in each section has a different length. So we are always looking for a length which has the average value in the on the wing. So for example, the maximum root chord here is in the root, the minimum is in the tip, and here we have actually an average value which we call standard mean chord. So a standard mean chord is surface area divided by wingspan. It gives us the average, the standard mean chord. So for example, if we have a simple rectangular wing shape, so the tip chord, the root chord was equal to our tip chord, and the lambda is equal to 1. So here, the standard mean chord for every part is equal to CT equal to CR equal to C. But if you have a tapered wing shape, as we saw here, so for example, if this is the half of the wing, so if this is a top view, This is the C of R, which is our root chord. This is a tip chord. So if I calculate the surface area divided by the wingspan, which is this length, if I show with the B, S divided by B, it gives me the standard mean chord. But we also have another chord, which is called mean aerodynamic chord. We show with the MAC, which can be calculated by this equation. So I don't need to know, I am not going to ask you about this equation, just show you the fundamental of how we can calculate the mean aerodynamic chord. So the mean aerodynamic chord here for a tapered wing shape can be calculated through this equation. 2/3 of the CR. The CR is going to be the root chord, and the lambda was taper ratio, right? So we talked about lambda, which was taper ratio. So this lambda was equal to CT, the tip chord, divided by root chord. So tip chord divided by root chord, it gives us this taper ratio. So these are the mean aerodynamic chord. I just wanted to again to show you this geometry, and you don't need to know none of this equation because it's going to be out of scope of this course, just to show you what's happening in the fundamental. So going back to the front view of the wing, we said that we can have actually the front view of the wing, which has a dihedral angle. So dihedral angle is the angle that airplane is making with this horizontal line. So from front view, we can have a dihedral angle, we can have an unhedral angle, and we can have the polyhedral angle. So the dihedral angle is this in this aircraft. If you see the wing, so these are actually have an angle from this horizontal line. So this angle, if I show with the gamma, this is dihedral angle. Some of the wings, they are downward, as we can see here. Again, this angle is downward. So this is called unhedral angle. And there are some types of the airplane, some part of the wing is straightforward, and the rest is going upward and creating an angle. This is called polyhedral angle. So these are different angles that we have from the front view of the wing. So the unhedral angle will include roll instability and improve the roll maneuverability. So what is the main reason of having this angle in the wing of the airplane? So I want to show you here as example in this airplane that we have here. So imagine that this airplane has an angle, right? So this airplane has an angle. If there is a wind disturbance goes to this airplane, so what would happen here? So if I have a side wind effects here, so this airplane, it will be tilted, right? So it will be tilted like this or like this, right? So if I have a wind here, so the airplane is going to be tilted like this. So now, once you are calculating the lift, we are always calculating the the projected surface area for the wing. So now once this airplane is tilted, so since you have the unhedral angle in this side of the wing, we have the higher projected surface area than this side. So we have the higher lift in the left side and the right side. So the airplane eventually get back to its original attitude. So going back again to the S slide, I want to show you here. So if you look at here, let's say that my wing has a dihedral angle. So this is, let's say, a dihedral angle, right? And this is my horizontal line. And let's say this wing has an angle of gamma here. So now imagine that you have a wind disturbance here and make your airplane unstable. This is a front view. So if I have a wind goes in this direction, so the wing eventually can become like, let's say, this. So the wing is tilted. So since this is a better picture, I'm going to show you here. So since we have the disturbance here, since our wing has a dihedral angle, so this is a half of my wingspan, and this is another half of my wingspan. So the lift which is generated in the left wing is going to be more than the wing which is, this is the left wing, and this is going to be right wing. So the lift which is generated in the left wing, left side of the wing, is going to be more than here, because we always consider a projected surface area. So this is actually the part of the wing that I have. So if I call this one the left wing, and this is the right wing, right? So here the length of the left wing is more than the projected of the right wing. So the length of the right wing times cosine of this angle. So I show the angle here with the gamma, or I'll show with this gamma here. So the left wing is equal to right wing, right? But once this is tilted, the projected surface area of the right wing is less than the left wing because of this cosine angle. So once this length is more than here, so it means that we have more surface area than here. So the lift which is generated in the left wing is going to be higher than this. So once the lift here is more than here, so it will create a moment which eventually return back the airplane. So this is again out of the scope of this course. You don't need to know too much about this material, but I just want to give you an overall view that why this airplane have this wing shape. So if I want to show you here, the lift which is generated in the left wing is going to be more than the lift which is generated in the right lift, in case that if it's tilted. So this would create a moment which would return back the airplane to the original reference line. So this is about stability in the roll axis. If you remember about this airplane, we said that this is going to be roll control, right? So this is going to be roll control. So if you want to have an airplane which has this angle, so this airplane doesn't have the dihedral angle right now, but if this airplane has dihedral angle, so if I have a disturbance in this side of the wing, this will be tilted, right? So then this projected surface area, if I project this, is going to be less than this side. So the lift which is generated left side is going to be more. So I have more lift here, so my airplane is tilted. So once the lift here is more than this side, this will be returned back to the original. And this is the main reason that we have this dihedral angle, specifically in the larger airplane, for the stability. So let me see if I can show you the flapping wing concept. So imagine that this has a dihedral angle. So if I consider this one's dihedral angle, if I have a wind comes here, if it is tilted, right? So the lift here is going to be more than here. So this will be returned back to original stage. So for anhedral, this is totally inverse, and we usually have instability because of this anhedral angle. The airplane that usually they want to be more acrobatic, they usually have this anhedral angle. Like if you look at the firefighter airplanes, like I mean some of the airplanes that they want to increase their maneuverability, they are actually going and they want to go faster, so they have this anhedral angle to be able to have a roll. So going to next slide. So the another important part, as we said, is the airfoil, which the airfoil is the cross section of the wing that I showed you as an example in one of these airplanes. So in the side view, we had the airfoil, we had the camber, thickness, and the twist angle. So this is the geometry of the airfoil. Once we get to the software XFLR5, I'm going to show you how you can design an airfoil and how you can create the airfoil. But this is the geometry of the airfoil. So this is called upper surface of the airfoil, this part. As we have this flash here, we also have the lower surface here. We have, this part is called leading edge. This part is called trailing edge. Any airfoil, if I connect the leading edge to trailing edge with this dashed line, this dashed line is called chord line. We also have a camber. My airfoil there is a point which I have the maximum thickness, and there is a point which I have my maximum camber. I can also have the upper camber and the lower camber. But these are, if my root chord or chord line has an angle with the horizontal or my related wing, this angle is called angle of attack. I will discuss more detail about this part in the software once we get there. So this is the side view of the wing, which is important, and it would create the shape of our airfoil. So again, airfoil has leading edge, has trailing edge, has the upper surface, has the lower surface, has a thickness, and a camber. And in case if our airfoil make an angle with the related wing or horizontal axis, this angle is called angle of attack. Again, I will talk more about this in more detail later on. So we also have the twist angle. We have two types of the twist. We have the aerodynamic twist and we have the geometrical twist, which we discuss later on. So this is an example of the twist. So if the angle of attack of our wing tip, this is the wing tip, be different by the angle of attack of the root tip, so our wing has a wing twist. So the main reason after having the twist on the wing or just twisting the wing is to want to change the lift distribution over the wing. We also have the coordinate systems in the aerial system. We discussed about three main coordinates. We have pitch, roll, and yaw. So if the airplane move around this is called pitch axis. If we move around this, it's called roll axis. And this is going to be yaw axis. So here, this is a normal axis. This is our aileron. These are other components of the airplanes that we discussed. Rudder, elevator. So we have the longitudinal axis. We can have lateral axis, and we can have vertical axis. So now going back to this example, to just show you again, if our airplane move like this, so this is moving around this point, right, which is called roll axis. If it move like this around this coordinate, this is going to be pitch, and this is going to be yaw. So these are the different axes that we have in our aerial object. So there are aerodynamic forces that they are acting on in any type of the airplane. There are four type of the forces that three of them they are aerodynamic. Another one is because of the gravity. So any airplane, the airfoil and the wing is in the fixing airplanes or drones. The wing and the airfoil, this is the airfoil that you can see, the cross section of the wing, are responsible to generate the lift force. Any airplane has a weight. Any airplane needs a thrust to be able to move in the air. This is a thrust force, and moving any object, the motion of any object in the air or any type of the flow, it will create a drag force, which is the resistance force because of the air. So we have the lift, we show with the L. We have the drag, we show with the D. We have the weight, we show with the weight, with the W, and we have the thrust, we show with the T. In order to have a stable flight all the time, lift should be equal to the weight, and the drag should be equal to thrust. So in this case, you have the equilibrium for your system, or your airplane will be stable. So lift is equal to weight, and the thrust is equal to the drag. So there are some flight conditions. So for example, if your airplane want to go up, so your lift should be equal to weight. If your planes want to go down, so your weight should be equal more than lift. If your airplane wants to slow down, for example, in landing, if you want to go to airports and airplane wants to land, so you want to get more drag to be able to land it. So drag should be more than thrust. And if your airplane wants to get accelerate, so your thrust should be equal to lift. So as I said, this equation, I'm not going to discuss about them, but if you want to go over them, this is actually shows that how airplane you can extract the equation for x-axis and y-axis of the forces which are acting on the airplane. This part is out of the scope of the course, and I'm trying to avoid as much as I can from the equations, and just I want to show you the fundamental or the physics behind of design of this unmanned aerial system. So force and moments, so any airplanes, we have lift, we have weight. The tail, since it has a surface area, is also generating lift. We have a drag and we have the thrust. So this is the vector balance for a glider. As we said, in a glider, we don't have thrust because we don't have any propulsion system. They are more reliable on the gravity acceleration. So for example, if this is a glider which is going down, this is a lift which is generated by this motion, and this is going to be component of the weight, which this component it generated thrust and makes this glider to move forward. So force and moment in the flapping wing drones is totally different. So this is a flapping wing. So we no longer have the propulsion system or motor with the propeller. In this case of the flapping wing, we usually have the actuation mechanism which goes inside of the body, like the birds, which they are using their muscles to create the flapping motions. So forces in the flapping wing is exactly like the fixed wing drones. This flapping motion, it generates the lift, also thrust, create the drag, and lift should compensate the weight. So lift is also equal to weight. So these are the different types of actuation mechanisms that we can see here. These are some equations that I just want to go over them. Since we will talk about the software, it's good to show you a little bit fundamental about what would happen here. So in any type of the airplane, we have the lift, drag, and the moment. So there are the loads that are acting on the airplane which cause our airplane to be able to fly. So the lift, the L is it stands for the lift. The rho is the air density. So the rho is, in all of these equations, is air density. The V infinity is the flight speed, is the speed of our airplane in different flight modes. So we can have different speed. The S is the surface area of the wing, or the wing area, that I showed you how to calculate the wing area. And we have eventually CL, which is the lift coefficient, as you can have here. We have CD is the drag coefficient, and CM we have the momentum coefficient. So the lift should be always equal to lift, should be always equal to weight. So lift is half of the air density times velocity of our airplane squared times surface area of the wing times the CL, which is the lift coefficient. So we are looking for the lift coefficient is lift divided by this half of rho V infinity S, which is called dynamic pressure. And the same for CD is the drag force divided by dynamic pressure. So here, for the airfoil, once you integrate the airfoil to the wing, the lift and the drag coefficient are different. So For the airfoil, usually we consider a third dimension goes to infinity. So this is the reason that we have a small cases of the L, E, and M here. But for the wing, since it has a finite dimension and the 3D, we have capital CL, CD, and CM. So this is going to be the first one for 2D case. Just consider the airfoil, and here we just have 3D case, which is going to be our wing. So this is wing, this is airfoil. So this was our today presentation and today lecture. I hope that you have enjoyed. If you have any question, please feel free to reach me with my email. Is mustafa.hassanalian@nmt.edu. Feel free to send me your question. I'm looking forward to that. So as I said, the fundamental that we discussed here is just for your information. I'm not going to ask you about that at all. I just want to show you the physics behind the aircraft design. So this was a different part or component of the wing that we discussed here. In the next lecture, I am going to talk about different parameters for aerodynamic analysis of the airplane, and then we jump to the airfoil, and then we will have 3 or 4 lecture to will just work with the software XFLR5 to run the simulation for our airplane. Thank you so much for watching this lecture, and have a nice day.